All right, hello, and thank you for watching. So today, we're going to talk about scheduling pods on nodes in a Kubernetes cluster. So real quick, what are we even watching here? Well, my name is Anthony Bushong, and I'm a solutions engineer at Google Cloud Platform, which means that I work with companies to get their workloads up and running, oftentimes on the Kubernetes and our managed Kubernetes offering container engine. So just making a series of quick reviews of Kubernetes concepts, one to help me learn the nuances in Kubernetes, and hopefully it'll be useful for other people trying to learn them too. So caveat, won't be starting at the very basics of Kubernetes. We'll just assume some basic familiarity. Cool, so here's a basic flow of working with Kubernetes. You have a set of containers that make up your application. You store them in a registry, and then in a manifest file, you're defining which containers you want to run and how you want to run them. Give that to the Kubernetes master, and it's off to the races. So let's take a look at what's actually happening. So one of the core components of Kubernetes is the scheduler. And the scheduler has a specific workflow that we have listed right here. So first, you create a pod. Then the scheduler notices that the new pod you created doesn't have a node assigned to it. So the scheduler goes through its own little song and dance, and then chooses a node for the pod, and then the pod is scheduled and up and running on the node. Sounds simple, right? Well, for me, it was a little bit complex to understand what was actually happening during that song and dance. So let's take a look at that. So first, the scheduler applies a set of predicates that filter out nodes where the pod should not run. So for example, if the pod spec contains some type of resource request for the containers, then the scheduler will filter out nodes that don't have at least that much resources available. Which really, side note, makes resources, using them wisely, very, very important and crucial to Kubernetes. So second, the scheduler then applies a set of priority functions. So what's happening here is nodes that weren't filtered out by that first predicate check, they are ranked in order. So the scheduler will take into account spreading pods across nodes and zones, and also try to favor least loaded nodes. And so after that, the node with the highest priority is then chosen, and if there are multiple nodes, then one of those are chosen at random. So for many use cases, this will do just fine. But what about people who are looking for more granular controls? What are some of the rules they have at their disposal that they can use to kind of influence the predicate check? So let's quickly talk through them, and then we'll see them in a demo. So I usually like to think of this problem from two specific user profiles. So the first is a pod first point of view. So basically, you want to tell a pod where to run in the cluster based on some type of based on a couple of different reasons. So the first is because you want you have specific VMs that you want the pod to run on, and that's where things like nodeSelector and nodeAffinity work out really well. Otherwise, another situation is you may want to co-locate the pod with other pods that it needs to frequently communicate with, and maybe you want to store them in the same zone. And so it doesn't matter which virtual machine, so long as the other pod is running on somewhere, kind of based on a feature like zones. And as long as that pod is running there, then enter podAffinity. So that's the first user profile. The second user profile comes from a node first point of view. So let's say you provision some special infrastructure for a specific workload. This could be for more resource intensive containers, or it could even be for workloads that require GPU acceleration. So let's say you've provisioned that, but you want to protect those machines from accepting other pods that it wasn't created to run. So that's where taints and tolerations come into play. So using taints and tolerations will allow you to taint nodes, meaning that no pod will be scheduled there unless it has a matching toleration. And so that's a huge feature that we'll see again in the demo. And one thing I want to add is that it's not a one-size-fits-all type of situation. There are a lot of use cases, and you probably will use these primitives and rules in tandem. So let's take a look at the actual demo. So we're going to see these in action on a Kubernetes cluster that will be running a machine machine learning workload amongst a few other workloads. And so specifically, we'll be deploying a containerized TensorFlow model server running the Inception model for image recognition. So I've provisioned some special virtual machines for that. So let's take a look at our cluster. So if you look here, I'm running Kubernetes in a Google Container Engine cluster. I have 2 node pools, one titled default pool and one titled dead pool. So the default pool has 4 1 vCPU machines, and dead pool, which is where I want to run Inception, has 2 8 vCPU machines. Yep, so we specifically made dead pool to run on Inception. So how do we ensure Inception gets there? This is how. So, well, a quick side note is that we'll be using Helm to deploy Inception. Helm is an awesome tool that's essentially a package manager for Kubernetes. So we're going to be using that to deploy a set of things into our Kubernetes cluster to run Inception. So how do we guarantee that the scheduler will put the Inception pod on one of the VMs in Deadpool? nodeSelector, we'll be using that. So this is the simplest form of constraint for scheduling. Basically, it specifies a map of key value pairs. So the pod will have a label defined as a nodeSelector. The label is just a key value pair. And then the node must have a matching key value pair as a label. And so those labels are then taken into account during the predicate check, and it should work. We should see that scheduled into Deadpool. So again, here you see that I've taken the basic Helm manifest and added a nodeSelector in the spec, and then I've given the nodes in Deadpool a matching nodeSelector label. And so if we actually look at that, we can see that in the manifest. So let's go to deployment. So here is my TensorFlow serving app. Great. If we look at here, I've added a nodeSelector and the key value pair. We have to go deeper because Inception, of course. And so let's take a look at the actual cluster itself. For the sake of time, I've already deployed a Kubernetes, I've already deployed Inception into the Kubernetes cluster. So let's look at where that's running. So pods are wide. Let's see the output here. So we see here that it's successfully, I have 1 pod running in Deadpool. Great, just as I wanted. And so let's look at that specific node and see to make sure that the nodeSelector is there, and actually look at the label associated with the node. So, oops, I need to describe that. Cool. So here's some information about our node, and here are the labels associated with the node. And there we go. We have to go deeper. So we see here nodeSelector, we gave the Inception pod a label, and we see the matching label, and that is how we got it running there. So awesome, cool. Worked exactly as intended, and that's great. But I also, again, provisioned Deadpool specifically for Inception, so I don't want anything else to run on those VMs. And so that's where Taints and Tolerations come into play. So again, Taints will enable the nodes in Deadpool to repel all pods away without a matching toleration, which is awesome because now all we have to do is give our Inception pod a matching toleration. And I think that, someone brought up to me, hey, why don't we just achieve this with podAffinity? But if we're deploying tens to dozens to hundreds of workloads into our cluster, it becomes really unwieldy to utilize anti-affinity. So it'd be really unwieldy to try and use anti-affinity to avoid the nodes in Deadpool. So we already gave the Inception pod a nodeSelector. Now we're going to give it a matching toleration for the taint that I gave to the node. So let's actually look at what that looks like on our node itself. As you see here, the node has a taint already existing because I gave it that. And so here we have a label. So we have dedicated equals Inception. That's a key and value pair. And in our spec, again, this is the same TensorFlow manifest. We see that we have a dedicated and Inception key value pair as a toleration, which is great. So now we know that not only is it selecting it, but the node will let it come through despite its taint because it has that matching toleration. One of the cool things is the effect here is no schedule, but you can also you can taint the node with the effect of no execute, I believe, and that basically will, again, you can taint a node running pods already, and all those pods will get evicted, which is unless they have a matching toleration. So again, useful for more use cases than just that deployment time. Great. And so one of the things I want to do, you're probably saying, well, we see that the node selector works, Anthony, but how do we ensure that the taint is actually, or the node and the taint it has are successfully repelling other pods? So I am going to take you up on that, and let's actually deploy 10 pods of just an Nginx container, and let's see where they get scheduled. So create, oops, actually I'm the wrong. Okay, so creating our Nginx deployment with the 10 pods, and great, we see that. Now let's look at the pods, see where they're scheduled. So here are all the nodes that they're running on, and you see none of them belong to dead pool, all in that other node pool that I showed you earlier called default pool. And that is effectively happening because we have tainted our dead pool nodes, and only the Inception pods have that matching toleration. So great, it works. So let's just delete that before we move on. Cool, so that's going to delete. Great, so now we have a matching taint and a node selector. I think we have Inception exactly where we want. But obviously, no one's going to be using a Kubernetes cluster just to run one type of service. And so let's say we have another service. This could be a front end that uses Redis as a cache or something like that. And so let's say let's start with one of the requirements, which is Redis. And we want to run, for whatever reason, we prefer that this run in a particular zone. So how can we do that? Enter nodeAffinity. So nodeAffinity is a property of pods that attracts them to a set of nodes. And so what's cool about this is we get a little more flexibility than nodeSelector, because now we can kind of have define a preference and then also narrow down, have a hard requirement and then a preference amongst the nodes remaining after that hard requirement. So as you see here, we are now going to be focusing on our default pool because we have tainted dead pool. Great. And so we see here that, I want to run this in US Central 1A. And so I actually have a multi-zone cluster here. So I have 2 nodes running in US Central 1A and 2 nodes running in US Central 1B. And so what can we do to ensure that this runs on US Central 1A? Well, Google Container Engine already gives us, it has labeled our nodes with the respective zone that it's in. So I think it makes sense to use that. So let's actually take a look at the, let's look at the nodes that we have. And so, okay, let's actually look into the Google Cloud Platform console and see which nodes are in US Central 1A, just so we can make sure that this nodeAffinity thing is working. So if we look, here's our default pool, and it's made up of 2 managed instance groups, which is just groups of like VMs in Google Cloud Platform. And so we see that this first instance group is in US Central 1A. And so we have nodes with a suffix of 0CMJ and 9P0S. So I want to make sure that Redis is running on one of these 2 nodes because it's, I don't care about which one. It's just the fact that it's in the same zone or in the zone that I want, US Central 1A. So let's look at what we've defined for Redis. Oops. So here's our Redis manifest. And you see here that I've described a nodeAffinity. And so here's our key value pair. We have the zone, and then the value is US Central 1A. Thank you, Container Engine. And then we also have a preference amongst those 2 nodes. So I've actually given a label and says prefer as the key and value is this. And so let's create that Redis. Actually, still in the wrong directory. Let's see. So we are going to create the Redis deployment. And let's see where that got scheduled. So great, there it is, 9P0S, which means it is successfully running in US Central 1A. We did it. Awesome. So now we want the front end to also be scheduled in the same zone as Redis because we need that cache, right? Well, for the for the sake of this demo, we theoretically could do achieve the same by using nodeAffinity, right? We can just do the same thing where we said, okay, just run in US Central 1A. But I do want to demonstrate one more rule that we have at our disposal, and that's podAffinity. So podAffinity is giving us so I again want it to run in the same zone. And so I'm using it to, rather than defining it at a node level, I'm using the pod label that Redis has first. So it is going to, so here's our podAffinity. It's actually going to look for a node running running with the label app equals Redis. And then the topology key is the zone itself. So it's basically going to say, hey, look for nodes with the running a pod that has app Redis. And then so long as it's scheduled on a node in the same zone as where that pod is running. So again, we'll kind of be looking for the same thing. Make sure that it's in either 0CMJ or 9P0S. So let's do create front-end deployment and see that in action. All right, great. So the front end is created. Let's see where that was deployed. Boom. Oh, it actually ended up on the same node. Very cool. So we see here that our front end is also running in US Central 1A, and we made that happen with the magic of podAffinity. So great. That was a quick demo of, again, all of the rules that you have at your disposal to, again, make sure that applications or pods and containers end up exactly where you'd like them to. The real special thing about that is keep in mind that Kubernetes is great for when you're running complex software that maybe you've decomposed into microservices, and it's great that they have a unified way of deployment and unified service discovery, health checking, load balancing, consistent things across that. But again, we still want to maintain some level of control of what type of resources those containers are running on and kind of where they're running. And so Kubernetes also gives us that, which is awesome. So one thing, did want to close up with a little treat, I guess. So I know I deployed Inception. I actually wanted to see some of the image classification it actually gives us and also prove that it works. So we're going to give it this picture. So while I'm doing that, let's look at, so we gave it a picture from Inception, and we see here some image classification that we got. And this is also, again, this is running in Kubernetes. We see the Windsor tie, suit of clothes. Very cool stuff. I need to look at Inception and TensorFlow a little more after this. I think this got me a little bit excited. But yeah, so that's it. Thanks for watching. I do want to encourage you to go check out some of the things that helped me learn this. One is Ian Lewis. He's a developer advocate with Google. He wrote a blog post on this stuff back in March when it was in beta with 1.6 for Kubernetes. And then also go look at Julia Evans's post on the scheduler. It's great stuff and really kind of dives into, again, that song and dance I was talking about. And if you're really feeling adventurous, go check out the actual scheduler application in the Kubernetes source code and kind of look at the predicates and priorities there. Cool. So thank you very much. Hopefully this was helpful. If you want to chat or give me feedback or just send me memes or whatever, you can @ me on Twitter. That's my Twitter handle there, AGMSBush. And yeah, thanks for watching.